The next speaker is Simon Müller from the project INTERSTORES with the presentation topic implementation of the expanding thermal source network as a step towards CO2 neutral industry. Simon, the floor is yours, please.
Thanks a lot. So thanks for the introduction. So yes, my name is Simon and I'm a researcher working at the University of Applied Sciences in Ingolstadt, Germany. And I'm happy that you decided to join today and listen to my presentation about a modern benchmark of an adaptive thermal source network. And we will see what that means in a second at an industrial site called the InCampus, which was already mentioned earlier by Michael Bayer. The research related to this presentation is part of the INTERSTORES project. As introduction, we will have a short look at thermal source networks in general. Afterwards, we will already dive into the specifics with the system description, and I also brought some examples about the envisaged operation, first monitoring results, and one exemplary planning step. Some of you might already know the concept of thermal source networks, short TSN, and the IEA-DHC Executive Committee defined them as networks that are mainly used as a source for heating and cooling by decentralized technologies such as heat pumps. A picture of that you can see on the right side. And there are multiple benefits of these systems, but I would only like to mention two right now, which are the low temperature levels of these grids, which makes integration of renewables easy, and the heating and cooling can be facilitated with the same infrastructure, which increases energy efficiency, and we will have a closer look of how that is achieved later. But with those two aspects of TSN, you can already see that they can help to move to a more climate-friendly future. And today we're going to take a look at the system, which can be seen in some parts as a modern benchmark of those TSNs in terms of retrofitting industrial areas, in terms of multi-source and multi-storage integration, and in terms of modularity and adaptability. The TSN I'm referring to is called the InCampus, and the InCampus is a planned 75-hectare industrial park, which will consist of up to 70 non-residential buildings. And the area of this project is situated in Ingolstadt, Germany. But before I show you some recent information about the InCampus and the related energy system, I want to have a quick look back in time and see what was happening at the InCampus before. Until 2008, the area we're talking about was occupied by a refinery, which started operation back in 1965, and sometime after the refinery shut down. The area was sold for €1 symbolic to the city of Ingolstadt and Audi, which is also located with its headquarters in Ingolstadt. Both partners agreed to plan to refurbish the area into an open technology park, and now we can already see that path from the old refinery site towards this new TSN system called the InCampus. And all of that process started with a soil remediation process to get rid of all the contamination that was left from the operation of the refinery, and 90% of the washed soil was again used on site, for example, for land leveling. And some of the gravel part that was washed will or is right now be used or utilized in the combination with old fire extinguishing basins, which you can see here, to build a seasonal thermal energy storage, which Michi Bayer mentioned earlier, which is part of the INTERSTORES project, which is pretty cool. So we're using pre-existing infrastructure to build seasonal thermal energy storages. Next to that, there are also groundwater wells, which keep the remaining contaminants from being washed away, and those can also be used as a thermal source or sink for the TSN, which you will also see later on. And now that we're all cleaned up, we can start with the current state. Currently, the InCampus is still under development. Overall, there are 4 construction phases planned to develop the whole area, but since September 2023, the first 4 buildings of the construction phase 1, which you can see here, went into operation and were connected to the TSN. The TSN infrastructure itself, on the other hand, is already installed, so pipes, or equipped for the following construction phases. It just needs new buildings to connect to it. And now we will have a closer look to the envisaged operation of the buildings and networks in construction phase 1. There are 12 buildings planned for construction phase 1, some office buildings, a security center where security features of cars are tested, and a data center, which has a significant waste heat potential. The demands of all those buildings in construction phase 1 sum up to around 7 gigawatt hours of heat demand per year and around 26 gigawatt hours of cooling demand. And what you see on the bottom of the slide are the projected load profiles. In blue, you can see the cooling loads with an offset because of the steady, more or less steady cooling needs of the data center, and in red, the heating demands. And you can see that a lot of the time those demands are overlapping, starting in September all the way through winter until mid of May. There is something which can be called balanced demand. This is the case when one of the buildings connected to the network has a heating demand and another building, because of its function or utilization, has a cooling demand at the same time. So in end of October, for example, the data center with its cooling demand will eject heat into the network via heat exchanger. And on the other end of the network, some office buildings with heating demands will extract some heat via the heat pumps. So instead of fulfilling the demands separately, the demands are balanced in the TSN. The primary energy demand is reduced and energy efficiency increases. For the first construction phase, it was projected that more than 10 gigawatt hours of thermal energy demand can be balanced throughout 1 year. For every demand that cannot be balanced, there is need for additional sources and sinks, which we can see here. We see the Danube River, we see additional recooling plants, and more to the south of the area, we see the groundwater wells, as mentioned before, all of which offer thermal power for heating and or cooling. Equally important or central to the energy system are the storage capacities. Here we see the firefighting water tanks in the energy hub, which are used as a buffer storage, and we have the network and surrounding soil as an inertia, and then the seasonal thermal energy storage, which is currently under construction but in the final stages of construction. And now we bring all of these components together, and we can understand the envisaged operation. In the center, there's the TSN, which is connecting all the different components of the energy system. Now, during winter, the buildings have a dominating heating demand, which is to some extent balanced by the waste heat from the data center. Additional heat supply can come from the thermal sources or discharging the S-TES. Now, during summer, the demands of the buildings change, and most of them will have a cooling demand, or you could also say they supply exhaust heat to the network. The waste heat from the data center does not really help with that, but adds even more heat to the network. Accordingly, all the surplus heat is either charged into the S-TES, which is just another way of saying there is cold discharge from the S-TES, or the surplus heat is discharged to the displayed heat sinks. That means, for example, groundwater wells or Danube are providing cooling energy, and that is why the blue arrow is directed towards the system. Yeah, before I mentioned that 4 buildings of the construction phase 1 went into operation 2 years ago now, and for those I can present some monitoring results starting in July 2023. You can see the summed up cooling demand of the buildings in dark blue. Right next to that, you can also see the cooling energy supplied by the groundwater wells in light blue. And you might recognize that the light blue bar of the supply is a little higher than the dark blue bar of the demand. This is because there are some cooling losses to the ground in these months. In May, you can see a more extreme behavior, exactly which is related to the temperature level of the network and the ground. Starting from October onwards, you can also see the summed up heating demands of the buildings in dark red, and next to that in light red, the heat which was supplied by the waste heat of the data center. And although the network temperature of the TSN is kept around 15 degrees Celsius in winter, there are still some heat losses to the surrounding ground. But as you can see, groundwater and waste heat can supply necessary thermal energy for the current system. And this is as far as I would like to go about the monitoring today. Yeah, but I brought some more insights into the technical project planning of the in-campus for reviewing the overall documentation of the project. The 5 main phases of the technical project development on the left were derived, and because I do not have the time to go in all to the chapters in detail, I brought one exemplary planning step, which is the comparison of different network types. There, the planning committee had a look at 1, 2, or 3 pipe systems and compared them to each other in different categories, more than are shown here. One of the highly weighted categories was energy efficiency, and it was correctly identified that a unidirectional 2-pipe system has some shortcomings compared to a bidirectional 2-pipe system in this regard. But from the point of view of the planning committee, the point was outweighed by the complexity of the control and complexity of the installation of the system itself. So therefore, it was decided to operate this system as a unidirectional 2-pipe system. Yeah, now we've seen a brief overview of the in-campus energy system, and in some details we were able to grasp maybe the benchmark properties of it. Originating from a former refinery site, the in-campus presented itself as a benchmark in terms of retrofitting. With the planned operation, we could see the multiple sources and multiple storages that are already included or will be included. And from the first monitoring results, we saw the system's operation in partial load now, but even more important that the energy system planning that considers the modular expansion and the integration of many more industrial demands in the future. And accordingly, future research will be oriented at maybe transferability of the system. And the first step in this regard is to analyze the planning process, which we did. So we have more steps ahead. Establish the energy monitoring to have a continuous report, not just once, and also go more in the direction of control systems, including the seasonal thermal energy storage, and maybe starting to have a MPC at the in-campus. Yeah, that would be all from my side. So thanks for listening, and I'm happy to answer questions in the chat or later in our Q&A session.